made some liquid oxygen. This is liquid nitrogen. You saw this on the first day of class. I brought in a big doer. You can kind of see it. It's clear. Okay, that's nitrogen. It's cold, cryogenic. That's what it's called. This here is liquid oxygen. I don't know if you can tell. Can you see it's kind of blue? It's a baby blue kind of color, really big, a cool looking baby blue color. Is this flammable? It's oxygen flammable. If I had straight up oxygen and there was a flame, would anything happen? Sort of. Only if there's something combustible would something happen. But if there's nothing combustible, nothing would happen to the oxygen. Okay, let me take this stuff out. So oxygen is only combustible if there's something to combust, like you or me. So in that case it would be flammable, but not in and of itself. So I want to be a little careful. Okay, this is a magnet. It's a supermagnet. So I need to cool it down to improve its magnetic ability. Now, do you notice that the nitrogen goes right through? Why is that? It's diamagnetic, as we just determined from the MO diagram. However, oxygen sticks. It's magnetic. From what we just determined from the MO diagram, we wouldn't have known that from Lewis. If I could pour it in there, it sticks right in the center. Nitrogen goes right through. You can even see it sticking to the side of the magnet as it evaporates. And it just sticks there. And yeah, liquid could be magnetic, respond to a magnetic field. This is paramagnetic. And that's the cool part about MO diagrams. We've never known this from Lewis. I think that's about the last little bit. Pretty cool, huh? And nothing went off or exploded. That's also cool. Nobody combusted today. Alright. Cool. So that's why this MO, one reason why this MO diagram stuff is pretty interesting. We can see why paramagnetism actually shows up to be real. And not just something that your chemistry instructor makes up. Okay. And likewise, liquid nitrogen, which is clear, don't need that. Okay. Let's turn this on. All right. I think everything's out. Just want to clean up, right? Okay. Did you want to see one more example? Would that be helpful? One more? Let's do one more. Somebody want to pick an atom for me? Who wants to pick an atom for me? Can't go higher than neon. Fluorine. An atom. People are saying like it's gassing and stuff. So for these examples that you'll see on your final, we're only going to do diatomics. Anything outside of that would be outside the scope of our class. If you're really excited about something like acetic acid, take Chem 110 and Chem 124. And they're on a year-long course. You're used to that because you're taking chemistry 2A, B, you're going to go to B and C. It'll be the same thing for those classes. You said fluorine. Now we're not going to go above neon ever. Why don't you give me a charge? You want that to be charged at all? Yeah. -1. Yeah. This would be a really normal sort of question. Though you picked an extremely depressing one, F and F minus. Not everybody's favorite letter right before finals. Right? Is this what song environment? Okay. All right, F and F minus. You could have put the minus over here, over here, doesn't matter. Doesn't matter to me. Okay, let's write out the electron configuration. 1s2, 2s2, 2p5, and then 1s2, 2s2, 2p6. Yeah. And remember, this would be the same as writing helium, 2s2, 2p5. And that's how I know. A couple people ask me, how do I know what's a core electron? When you write the electron configuration, anything from the previous noble gas is considered a core electron. So I don't have to include in our examples the 1s. Okay. So let's write out the energy levels down here. I'm going to skip, again, the 1s. So we're going to go straight to the 2s and the 2p. Skipping the 1s again, core electron. Okay? Maybe we can almost fit everything on the screen. The 2s, every part has a bonding, low energy, and an anti-bonding. And hopefully, after you do a number of these, you'll see, oh, it's the same every time. Diagram's always going to start looking the same. And that's why people, other students like yourself, by the end of the quarter, like these kind of questions, because you're just doing the same thing every time, just following this template. Okay? The 2p, now you have to think a little bit. Okay, that's fluorine. Let me show you this picture. The fluorine 2p's look like this. They have the pattern of 1, 2, 2, 1. Okay? If it was nitrogen or lower in atomic number, it would be 2, 1, 2, 1. So we're going to follow the fluorine. It's the only thing you'd really need to know here. So that's 1, 2, 2, 1. Okay, there it is. I can name these levels already. I know if it's a single line, it's a sigma. It comes from a 2p. If it's a double line, it's a pi, and that comes from a 2p. Double line pi, 2p, and it's on top, so I know it has a star. And a sigma comes from a 2p, and a star because it's on top. So the same kind of thing you saw me do last time. The only thing that's really going to be different is the number of electrons. From the other example, the only difference again, number of electrons. By the way, those in the back, if you want a seat, there's plenty of seats up on the sides, but if you need a quick back sit, because you'll have to can't stand this stuff, I totally 2s2, and on the left it's 2p5. 1, 2, 3, 4, 5. 2s2 on the right-hand side, but 2p6. 1, 2, 3, 4, 5, 6. Okay. Let's do the bottom picture first now, filling in the electrons. I'll zoom in a little bit. 2 on each side, total of 4. 1, 2, 3, 4. Top picture, there's 5 on the left, 6 on the right, total of 11. Again, if you're having trouble filling these in, you can watch my pen here. 1, 2, and then go up. 3, stay unpaired, 4. Then pair, 5, 6. Go up top, unpaired, 7, 8. Pair, 9, 10. And then unpaired, 11 up at the top. If there was a 12, it would pair right there. Para or diamagnetic. Yep, you got it. Paramagnetic. Because of that one single unpaired electron right there. On order. What's our first number? 6. That 6 comes from, just to illustrate this, these. Okay? Minus what? 5. Just to illustrate that, 2 comes from these. Okay? 6 minus 5, that's 1/2. Can't draw this and do this. Half bond, and sorry, I do not have liquid fluorine 2 minus support through my magnet. But it would be magnetic as well. It's just like previous. Any questions on this? Yeah, you gotta get used to the pattern, and you will, by the time of the final, should consider this a pretty easy problem. It would be a free, I don't know if it'll be worth 20 or 30 points, but it's basically a free 20 or 30 points. That's why you should consider it. And right now you're like, oh my gosh, I'm gonna freak out. Don't worry, the other classes are like hitting their heads against the wall too. You know? It's not just you. In the textbook, on page 420, you see this picture. It has every neutral example done for you already. On the final, you're going to see something between lithium and neon. It could be uncharged or charged. So you already know the possible examples. You could sit down with you and your cousin, your uncle. They can give you an example. You can try to draw it out for them. And on this page, it also has listed the bond order and the magnetism. So all that's pretty set for you. Okay? So just to let you know that exists, and you can take a look at it. I have YouTube examples, molecular orbital, I believe 1 to 4. They can take a look at if you want to see me doing other examples. All right, don't worry. I know you're thinking, oh my gosh, we have more time. Can't we talk about more stuff? Oh yeah, definitely. We're going back now. We finished. That was one section. If you didn't realize it, that was section 5. That was the last hardest section in the class. Relatively, the rest of the section should be a little easier. We're going to do section 10-2, dot, whatever, 2 through 4 sort of together. And this in the reader is page 105. And in the textbook, we're kind of going backwards a little bit. Remember, I did a little out of order of the text. So if you're curious on the textbook, let's see, we're going back to 400. The reason I did it out of order is the ideas we use now in these next sections actually build on the MO theory, so I thought it made more sense to do that first. And then it's not as depressing to end on the freaky stuff last, you know? Okay, so 2 through 4. Let's take a look at carbon. Carbon is 1s2, 2s2, 2p2. So let's say I had CH4. If I drew the Lewis structure for this, I would get this molecule. A tetrahedral molecule. It's like that. Bond angles, 109.5. Okay, so all those bond angles, 109.5. Here's the problem. If we look at the electronic configuration, let's take a look at these. These are s orbitals, they look like spheres. This is a p orbital. Looks like this, or it can go forward and backwards, or left and right. If we stick those together, we don't get 109-degree bond angles at best. If we put 2 p's together, you get a 90-degree bond angle. So if we are merely taking the atomic orbitals and putting them together, doesn't get the bond angles we expect. We expect 109.5, but if you put, say, 2 p's together, they'd be at 90 degrees. So here, this gives us 90 degrees at best bond angles. Not, and that's a discrepancy with the 109.5 that Vesper tells us. This is essentially valence bond theory. It's a theory of bonding where you just stick orbitals together and figure out the bond angles, which works sometimes, but not all the time. Here's an example where it doesn't work. So valence bond theory, which is a theory, I'm not going to say anything else about it. I have a YouTube video about it if you want to see it. But valence bond theory doesn't give us the right angles that Vesper tells us, and Vesper agrees nicely with experiments. So we want to figure out what's going on with these orbitals that give us these angles. Okay? That's what this next section is about. Anybody or anybody's parents have a Prius? Yeah, that's a hybrid. And that's what happened. That happens in chemistry too. In the Prius, you're mixing or you're hybridizing an internal combustion engine with batteries. Okay, you're mixing the two. We call that a hybrid. The same thing here, but now in chemistry, we're going to mix orbitals and make a new type of orbital that prior to this point did not exist. Okay? Let me show you how that'll work. And this will be called hybridization. Hybridization. Focusing on this example here. The energy level, kind of like what we did before, but we're talking only about atoms right now. I'm not going to draw the 4 electrons, which are the 1s, just like before. Okay, so we're not drawing the 4. Just the 2s and the 2p. Let's draw on those electrons. 2s2, 2p2. 2s2, 2p2. What we're guessing happens is the following. We're guessing these hybridize to make new orbitals. 4 new orbitals that are 1 part 2s and 3 parts 2p. Because we're mixing 3 2p's with 1 2s. So it's going to be 1 part s and 3 parts p. Thus, we have the genius name of sp3. Because there's 1 of the 2s's and 3 of the 2p's. We have a total of 4 electrons. 1, 2, 3, 4. 1 electron for each orbital. What we're thinking happens to the orbitals is the following. If I just take a simple example, an S, and I add this to a P, to make a new kind of hybridized orbital, these, I would have something like, I'll draw that S in a different color here. Let's draw a black. The unshaded parts would add, and the shade with the unshaded would subtract. Make something that looks like this, a big fat lobe with a tiny little lobe. Something like that as a new type of orbital we call a hybridized orbital. Now let me show you an artistic rendering. Okay, this is just me, lame stuff. I'll come back to this in a moment. What we're doing, and this is a figure from your textbook. There's something like it in the reader, but this is precise, kind of like the figure in your textbook on page 403. We're taking an S and 3 P's, we're mixing together, stirring it a little bit, putting it in a blender, and we're coming up with 4 new orbitals, like what I just drew. And guess what? Magically, mathematically, scientifically, paradoxically, those have 109.5 degree bond angles. Okay? So, when you mix 1s, remember these are mathematical functions. From chapter 7, remember that crazy psi wave function at the radial and the angular part? Those are these, those are wave functions. Mathematically, if you put those together, you get these. Just adding functions. And when you put them together, it turns out that the hybridization fits the theory of Vesper, where you get a tetrahedral shape with 109.5 degree bond angles. That's where if you mix 1s and 3 p's. This is our guess of what we think is happening, okay? That there's a hybridization. Okay? This is called sp3 hybridization. It is a type of hybridization. Let's do another one. Oh, I hear the sounds of joy coming from people. kind of molecule, if I draw the Lewis structure for it, would look like this. This is trigonal pyramidal, or trigonal planar. So the bond angles are 120 degrees. Oh, yeah. Close your eyes for a second. There. Okay, 4 hydrogens. All right, for C2H4, we have this kind of shape, 120 degree bond angles. It can't be the same hybridization that we just saw, because the previous type of hybridization gives you the tetrahedral shape. We need a different type of hybridization for this to happen. So here's our best guess at what happens here. Same starting point for carbon. (2s and 2p). Same starting point. But we think it hybridizes differently. It has to, because we need 120 degree bond angles. And how do we get that? Well, what we think happens is one of the S and 2 of the P's hybridize, and one of the 2 P's stays untouched. So one of these 2 P's right here doesn't move, it just stays as is, and keeps its electron. And we think the other 3, these 3, hybridize to make 3 new orbitals. So the 2p is untouched, and we make 3 new orbitals. Because it's 1 part S and 2 parts P, we have this genius name that's S, or 1 part S, 2 parts P, sp2. Okay? Because it's 1 of the 2s and 2 2p's. So what we're talking about, I'm going to move this for just a moment. I'll put it back. Taking 1 of the S's, mathematical functions, 2 of the 2 P's. We're going to add those functions together, see what we get. We get the following, and then magically, amazingly, mathematically, they turn into 120 degree bond angles, trigonal planar. Okay? So this kind of hybridization turns out to the shape that we see experimentally. And so thus kind of confirms our theory, gives us hope that this is the hybridization that's occurring. Form this kind of hybrid different than before, but one of the 2 P's doesn't play, stays separate. Okay? This question? Yeah. Olivia. Why is there 1 2p up there? Again, okay, there's a couple ways you can answer that. One is, the 2p stays up there. If it does, then we get the hybridization that fits the shape. So that's nice. I can answer your question a different way, though. Let's say this carbon, the one on the left, I'm drawing that shape that you saw right in this picture here. That shape? Okay. That carbon bonds to another carbon over here. That has that same thing. At the bond angles we expect. Okay. Each one of these has 1 electron. 2 here, because each brings 1. Okay, the H's are what orbital? Let's draw the H's. H's are 1s1. That's the circle. They bring an electron. Two electrons form up 1 bond. But you notice the problem is, by the way, what kind of bond is this? That's a sigma bond because it happens between the center points. Where sigma from before happens between the center. It forms a sigma bond. These are all sigma bonds. But remember from the original picture, there's two bonds, not one. Two, not one. Well, that's where the 2p comes into play. It forms a perpendicular. Each one of these has a perpendicular 2p orbital. And I've drawn this really expanded out. These would actually be overlapping and touching. So these are touching. What kind of bonds do these two p orbitals form? What kind of bond is that? That's a pi bond. And there's your double bond. So that leftover p orbital actually helps to form the pi bond, causing now a double bond. Sigma bonds are much stronger than pi bonds, and so that's why a double bond is not twice as strong as a single bond. Yeah.
Does it have to be the first 2p that stays untouched?
Does it have to be the first 2p that stays untouched? No, not necessarily. It doesn't matter, but it's a 2p that keeps an electron. Yeah. You wouldn't have to duplicate this. I will do examples later that you can see what you have to do here, but you would have to identify sigma or pi bonds.